So as we zoom in, we keep going, and now this red splotch that you see there, that galaxy, that's a galaxy. That galaxy is more than 33 billion light years away. It's amazing, it's only 320 million years after the Big Bang. So we can actually measure things like how fast it's forming stars. We can measure the amount of stars in the galaxy. We know the size because we know how far away it is. And we know the typical age of the stars in the galaxy, so we know a lot.
The implications of these findings ripple across the field of cosmic archaeology. The high contamination rate among the brightest candidates, an estimated 67%, highlights a fundamental limitation in our search for the universe's primordial structures. Even JWST's powerful infrared eyes can be misled by the clever disguises of dusty, relatively nearby galaxies. This means that for every genuine ancient galaxy uncovered, many more are likely imposters, and only the most rigorous analyses, combining different wavelengths, advanced software, and the painstaking acquisition of spectroscopic data, can reveal the truth. Yet far from diminishing the importance of early galaxy discoveries, these results make the confirmed survivors all the more extraordinary. In a universe teeming with dusty lookalikes, true ancient galaxies become rare jewels, evidence of cosmic processes that shaped everything we see today. Each one we confirm is a witness to the dawn of structure, a beacon illuminating the chaotic, creative fires that forged the first stars and galaxies. The study also illustrates the limitations and challenges of even our most advanced instruments. The main sample was selected for brightness, meaning fainter early galaxies, perhaps more typical of the young universe, remain largely unexplored. The direct spectroscopic confirmation, vital for absolute certainty, could only be applied to a small fraction of candidates. As a result, while the brightest and most massive early galaxies are the easiest to spot, they may not represent the broader population of the universe's first light-bearers. Nonetheless, the methods and insights from this work are already shaping the strategies of future space missions. Astronomers now know they must be cautious when interpreting the brightest, reddest objects in their surveys. They're refining their techniques and seeking out new ways to separate genuine high redshift galaxies from imposters by combining data from multiple telescopes, leveraging advances in artificial intelligence, and designing new spectroscopic campaigns to probe deeper and with greater certainty. Behind the scenes, the study's success also reflects the collaborative spirit of modern astronomy. The analysis relied on public data from JWST's surveys, covering 4 blank regions of the sky that together span an area roughly equal to the full moon. Support came from major research grants and the efforts of scientists and engineers across institutions. It's a testament to the power of shared resources and open data, enabling discoveries that stretch our imagination to the very edge of time. With each new confirmed ancient galaxy, we peel back another layer of cosmic history. We glimpse the universe not as it is today, but as it was in its wild, youthful beginnings, a time when the first galaxies blazed into being amid darkness, and the story of everything we know was just beginning to unfold. As our quest continues, the lessons of JWST remind us the cosmos guards its secrets closely, but with ingenuity, patience, and relentless curiosity, humanity is learning how to unlock them. But even as we celebrate each new discovery from the James Webb Space Telescope, this latest study reminds us that the cosmos can also be a master of disguise. Out of the 300 exceptionally bright galaxy candidates that astronomers selected using the sophisticated dropout technique, only a tiny fraction, about 7%, may be true relics from the universe's earliest billion years. The rest, it turns out, are mostly cosmic masqueraders, galaxies much closer to us in space and time, whose dusty veils make them appear as if they belong to the ancient dawn. The challenge, as astronomers have found, lies in the deceptive power of interstellar dust. When we peer across light years and eons, both truly ancient galaxies and certain nearby dust-enshrouded galaxies can appear strikingly similar. The redness in their light, so crucial for identifying the universe's first galaxies, can arise either from the stretching of wavelengths over vast cosmic distances, or from dust grains scattering and absorbing starlight right here in our cosmic neighborhood. To even the most advanced infrared eyes of JWST, these imposters can be nearly indistinguishable. To separate the genuine ancient galaxies from their look-alike counterparts, the research team combined the classic dropout technique with cutting-edge light analysis. They meticulously sifted through data from 4 major survey fields, covering an area on the sky as large as the full moon. Only the brightest candidates were chosen, those whose luminosity, if truly ancient, would mark them as some of the most extreme galaxies ever seen from the dawn of time. What they found was remarkable. The data pointed to a planet roughly the size of Saturn or Jupiter, orbiting Alpha Centauri A at a distance where temperatures would average around 225 Kelvin, that's minus 48 degrees Celsius, or minus 55 degrees Fahrenheit. Chilly, to be sure, but not out of the question for habitability, especially if this gas giant hosts large moons with more temperate environments. The planet's orbit appears eccentric, taking between 2 and 3 Earth years to complete a single trip around its star. While it's unlikely that life could thrive in the swirling clouds of a gas giant, the real prize might lie elsewhere, perhaps on a rocky moon, warmed by its parent planet's gravity and the gentle rays of Alpha Centauri A. Just as Jupiter and Saturn in our own solar system are orbited by fascinating moons like Europa and Enceladus, this newfound world could have companions of its own waiting to be discovered. For scientists, the significance of this discovery is profound. Alpha Centauri is our nearest interstellar neighbor, making any planets there prime targets for future observation and, possibly, exploration. The James Webb Space Telescope, already renowned for peering into the most distant reaches of the universe, has now proven its mettle in our own cosmic backyard. By developing custom observing sequences and pushing the limits of their technology, the Webb operations team has opened a new chapter in our search for habitable worlds. What makes this discovery so stirring is not simply that a planet may orbit Alpha Centauri A, but that it demonstrates just how far astronomical science and instrumentation have come. Until recently, the glare of a G2V star like Alpha Centauri A, so similar to our Sun, made it almost impossible to spot planets in its habitable zone. The overwhelming brightness would drown out any planetary signals, making even the most sensitive telescopes struggle to tease out the faintest hint of a companion world. But with the James Webb Space Telescope's coronagraphic imaging and the ingenious use of a reference star, astronomers were able to peel away the overwhelming light and isolate the subtle presence of an exoplanet. The planet itself, inferred to be a gas giant roughly the size of Saturn or Jupiter, orbits within the star's habitable zone, a region where, in theory, liquid water could exist on a planetary surface. While a gas giant of this kind is unlikely to host life as we know it, the prospect of moons orbiting this planet, moons with rocky surfaces and atmospheres, ignites the imagination. In our own solar system, icy moons like Europa and Enceladus have already shown tantalizing signs of subsurface oceans, and Titan has an atmosphere rich in organic molecules. The possibility that Alpha Centauri A's newfound planet might have its own system of moons, perhaps even a rocky, water-rich satellite, gives scientists a compelling target for future study. But science is rarely straightforward. The elusive planets seem to flicker in and out of view, visible in one set of Webb's observations, then vanishing in subsequent passes. This led to an intense period of data analysis and computer modeling. Millions of possible orbits were simulated to explain the planet's ghostly appearances and disappearances. What emerged was a solution. The planet's orbit likely brings it close enough to Alpha Centauri A at certain points that it is lost in the star's brilliance, only to reappear as it swings outward once more. This orbital eccentricity adds another layer of fascination, suggesting a dynamic and possibly complex planetary system. Alpha Centauri's significance extends beyond this single discovery. This triple star system, with Alpha Centauri A and B, resembling our Sun more closely than any other nearby stars, and Proxima Centauri already hosting multiple planets, is a cosmic laboratory just 4.34 light-years away. Each new detection in this neighborhood isn't just an astronomical milestone, it's a stepping stone toward understanding how common planetary systems like our own might be throughout the galaxy. Detecting planets around bright, sun-like stars is essential for one of astronomy's greatest quests, finding a truly Earth-like world. Most of the thousands of exoplanets discovered so far orbit red dwarfs, which, while abundant, pose challenges for habitability due to strong stellar flares and close, tidally locked orbits. Alpha Centauri A, by contrast, offers a familiar stellar environment. If planets orbiting such stars are common, and if they include rocky worlds in the habitable zone, then the prospects for life elsewhere become even more intriguing. The methods pioneered in this search, coronagraphy, reference star subtraction, careful elimination of false positives, will now be applied to other nearby sun-like stars. The Webb team's success here paves the way for a new era of exoplanet discovery, where detecting a planet around a star like our own is no longer a distant dream, but an achievable goal. In the years ahead, astronomers will continue to monitor Alpha Centauri A, seeking further confirmation of the planet and searching for additional worlds that may remain hidden in the system's dazzling light. Ground-based telescopes, future space missions, and perhaps even direct imaging with next-generation observatories could soon reveal even more about our stellar neighbors. Imagine a future where robotic probes, powered by advances in propulsion and artificial intelligence, are dispatched to the Alpha Centauri system. The detection of a potentially habitable moon or a rocky planet would provide an irresistible target for interstellar exploration. Even now, projects like Breakthrough Starshot are being designed with Alpha Centauri as their destination, aiming to send tiny, high-speed spacecraft to our nearest stars. This discovery is a testament to human curiosity and technical brilliance. It reminds us that even the nearest stars hold secrets waiting to be uncovered. The light from Alpha Centauri has shone in our night sky for millennia, but only now are we truly beginning to decode its story. As we continue to gaze outward, each new planet found, each new technique mastered, brings us closer to answering some of humanity's oldest questions. Are we alone? Is Earth unique? Or is the galaxy teeming with worlds like our own, orbiting suns that once seemed forever out of reach? The hunt for habitable worlds is just beginning. With each discovery, the universe becomes a little less mysterious and far more wondrous. If you enjoyed this journey through the latest discoveries at Alpha Centauri, make sure to like this video and subscribe for more content like this.